I just made some adjustments to the notes here. So gamma is what I'm going to call this flow variation, which is the difference in pressure drop between the bottom of the stack and the top of the stack relative to the total pressure drop. In the example we've been working through, we get that the radius, if we think of it as a circular pipe, that radius is going to scale as the pressure drop to the 1/4 power, also to the height to the 1/4 power, and to gamma to the 1/4 power. So if gamma is fairly small, the radius is going to become bigger. What I wanted to go into a little bit more depth is what dictates the height of the stack. How did I get this 18 centimeters? And also just want to show a few simulations to try to assess how serious a problem this really is. If we think about flow variation in a stack, what do we expect that to do, both for the air side and the fuel side? And what are some of the constraints, and what are things we can do to engineer or try to balance these things? So first of all, a little bit about stack height. The stack height, of course, depends on how big the interconnects are, how thick they are, how much gas space we're leaving on the air and the fuel side. But just to make some estimates, with these 12 by 12 cells, we're getting an electrical power of 18.6 watts per cell, according to our 1D stack model. This is operating at 80% utilization and 0.7 volts operating voltage. So if we hold to that, then we can calculate the number of cells that we need. This would be 20,000 watts divided by our 18.6 watts per cell. It's 1075 cells total. So if we think about the number of cells per stack, which we've been calling M, that's dictated by the voltages we want to generate. So we wanted to make 380 volts in this example, and we're operating the cells at 0.7 volts. So that's a total of 540 cells, which conveniently is about half the total number of cells we need. What this is telling us is we would need 2 stacks if we're using cells of this size. But let's also think about the size of this. So it's 12 by 12 centimeters, but if we had, let's say, a 1 millimeter thick interconnect, we talked about a 1 millimeter thick air channel, say we had a 1 millimeter thick fuel channel as well, and just ignore the cell thickness, it's pretty thin. So that's about 3 millimeters. So if we take that 0.3 centimeters times 540 cells, this would be 160 centimeters, or 1.6 meters tall. So we're talking about a stack which would be like, you know, a person's height, right? And it's only 12 by 12 centimeters, and it's 1.6 meters tall. Not really. I think what you might do in that situation, either you jump to some newer, bigger cell. That's an option. And I think, realistically, 12 by 12 centimeter cell is pretty small by today's standards. So I think that would be one avenue of investigation, is like, well, maybe we can work with a 6 by 6 inch cell. Those are some things that people manufacture. Cirrus, I think, works with 5 by 4 inch cells, and then they have another size which is bigger than that. And so we might look at sort of what things are manufacturable today and then try to resize our stack accordingly. Another way to do this is to break this up into multiple stacks. So that's one thing we talked about already was, could we take this and make it shorter? And in particular, if we had a 9 by 9 array in series, electrically in series, we could reduce H to 18 centimeters. And so we'd have 9 times 18 centimeters. Its totals are 160. centimeter stack. That is sort of getting more into the realm of, reasonableness. So stack kind of, we want it to have kind of similar aspect ratios. So we 12 by centimeter by 12 by 18. This is something we can imagine building. So that's where the H equals 18 centimeters came from for that calculation. And so then also to remind you, the total number of cells, M, is 60 cells. And so if we think about the total fuel flow, this would be 60 cells times the flow rate per cell. And we've been modeling one cell, which had 4.3 times 10 to the minus 5 moles per second. So N dot total of fuel is 0.026 moles per second. This is to the stack as a whole. If we take that total fuel flow times the air to fuel ratio, which was 36.9 as I recall, this would be the total airflow. Now we can sort of plug this into our model to sort out what the pressure drop is vertically, and that's what we did. So let's talk a little bit about the tolerance to flow variation. In this case, we were talking about air. I picked sort of 5% out of a hat, but is that really true? Like if the air flow variation is 5%, is that a bad thing? So one of the things we can do is use our 1D simulator to kind of address that problem. I'm going to start a little table. Let's look at airflow variations and what happens to our cell. The first thing I'm going to assume is that there's nothing going on with the fuel. So the air ratio is what's changing in this case. Our nominal ratio is 36.9 is what we calculated. And under these conditions, we had an outlet temperature of 750 degrees, because that was, of course, at that time was our input to the problem. And we also prescribed a voltage in volts of 0.7 volts and a utilization of 0.8. And this was for a fuel flow of 4.3 times 10 to the minus 5 moles. And a current we found was 26.6 amps, which is dictated by Faraday's law. And then we calculated a length of 12.4 centimeters. So that's just a summary of our calculation. So now imagine we start messing with this, and we're keeping the cell size the same. So now we want to keep this the same. The other thing is we're presuming that the fuel is unaffected by things going on in the air side. So the fuel flow, it's going to be the same. Presumably, we're also keeping the utilization the same. So these are all things we can kind of control and keep fixed. And if we're keeping the utilization the same and the fuel flow is the same, the current is going to be the same too. Recall the air is in massive excess because we're using it as a coolant. So we're not going to run out of oxygen. So now we start lowering the air ratio, and I'm imagining we start lowering it, say, by 5% increments. So imagine we lower it to 35, 33.2, 29.5. So if I look at gamma, this would be 0, 5%, 10%, 20%. The tricky part is when we resimulate it, we somehow have to constrain the overall length of the cell to be 12.4 centimeters. And we're also constraining utilization and fuel. So what's the degree of freedom here? What is going to be variable? And one thing to keep in mind, we don't control the voltage of individual cells because they're all in series. So if one has higher resistance than another, it'll have a different cell voltage on it. So it'll break the symmetry. It's actually the current through the whole stack is fixed. And so what actually varies is the voltage. The cell voltage now can drift away from 0.7 volts at the same current because the temperature is changing, because the airflow is changing. So that suddenly becomes one of the variables we're going to solve for. Okay, so here's the spreadsheet model. I've changed some of the color scheme. So I've changed the N dot, the air to fuel ratio to purple, because I'm now not going to iterate on that. I'm actually going to define that. In this case, at a 20% flow variation, we have a 29.5 to 1 air to fuel ratio. I'm keeping the utilization the same because we're passing the same amount of current. So our extent of reaction is the same, feeding the same amount of fuel, and we're utilizing the same amount of it. But what can change is the outlet temperature. So I might know I'm feeding in at 550 C, but now I have less cooling. So I expect the temperature of the exit exhaust to be higher. And I'll show you in a second. It's resolved this and calculated a value for 770 degrees C. And it's also adjusted the voltage to make all the energy balance work out, and also constrain the length of the cell to be 12.4 centimeters. The way I did this, remember, we were using goal-seek to do the energy balance and the reforming calculation. And we did that because we were solving for the airflow, and we knew the exit temperature. So we could do that as a separate calculation. And then use solver just for the part of the calculation where we had to determine the internal temperatures of the stack. Instead, what I've done here is I've said, well, I have to use solver to solve these temperatures internal to the stack. And so I'm still going to try to drive this sum of square differences to 0 for the energy balances. But I'm going to try at the same time to solve the stack energy balance and the exit temperature and the voltage. And it's pretty straightforward in solver to do that. You can add more constraints and you add more variables. So the additional constraints I'm adding is I want the reforming equilibria to be obeyed. I want the stack balance to be obeyed. And we want the cell length to be 12.4 centimeters. So what I've done is down here, I have typed in 12.4. That's my target length. And I've defined the difference between the calculated length and the desired length. This cell now contains an objective function, which should go to 0 as the cell length goes to the desired cell length. And so now over here, I've just put in a composite objective function. Basically, I'm taking the sum square difference here for the internal temperatures, and I'm adding to it the sum square difference for the cell length. So I'm forcing that to go to 0. I'm also adding to it the objective function for the reforming equilibria. So this is cell as well. So this cell is the length. This cell is the reforming equilibria. And then one more, we have the energy balance. Energy balance has to be obeyed too. So I've taken all of those objective functions, which are supposed to go to 0. I've squared them. I'm adding it to the previous sum of squares for the energy balance on each subcell individually. And that whole thing has to go to 0. And so what you can do now is we can adjust the air to fuel ratio. And that's what I've done here. I've made the air to fuel ratio, instead of 36.9, I've lowered it in this case to 29.5, which represents a 20% reduction in the airflow. And then run solver on this objective. And it looks like this. So tools, solver, that cell. And then if I look at all the cells I'm varying, outlet temperature, cell voltage, and all these guys, and the reforming equilibria, it's now adjusting all of those until all the objective functions are obeyed. And since I'd already solved it, it was quick. But here's the answer. It says that at this 20% lower flow, we're going to get an outlet temperature of 770 C, and the cell voltage will also go up a little bit to 0.74 volts. So we actually get a little bit more power out of the cell because we're operating it at a higher temperature. If I fill in some of the blanks here of what we're actually calculating, we get a little bit of cell voltage variation, but mostly what we're seeing is changing outlet temperature. So the bottom line after all this is that a 10% flow variation is translating to about a 10 degrees C exit temp variation. How big a deal is that? 10 degrees C is not very much if you're up at like 750 degrees C. It's not unusual for SOFC stacks to be operating over 50-degree fluctuations in the exit temperature. So it's possible we could tolerate quite a lot of airflow variation, which means that if we took that 2-inch hole that we made to lower the variation to 5%, we could let that loose a little bit. So let's say we allowed 20% variation. That would be a 20-degree increase in temperature at the top of the stack relative to the bottom. If we wanted to make it 50 degrees, kind of projecting here, we'd probably be talking about flow variations of getting up to 40 or 50%. So kind of going back to this equation that we derived earlier, what's the impact of that? So let's say, imagine, we allow this this flow variation parameter gamma, instead of being, 0.05, let's say it was more like 0.2 or 0.5, right? So we're talking about factors of maybe 5 or even 10 inside this 1/4 power quantity. How much does that change the radius? So imagine I take the same quantity that I just calculated and we make the flow variation 50% instead of 5%. I put that in the denominator. We're going to have 10 times bigger. So I'm going to take 10 to the 0.25 power. The radius comes out a factor of 1.7 difference. So because this fourth root dependence, it has a very weak impact on the allowable manifold size. So still going to have to make room for these manifolds. Okay, so that brings up another question, is what else could we do? Like if we wanted to minimize these manifold size, we can look at this equation and sort of try to figure that out. It depends on the height, which may be more of a manufacturing constraint. We could certainly make the stacks a lot shorter. Having a pancake sort of shaped stack means you're going to have many, many stacks with lots of end plates. So you start to lose the advantages of having a stack in the first place. So I don't think there's much room there. So we look at everything else in here, there really isn't any other degrees of freedom. The only one is delta P0, which is the pressure across the stack or across each cell. To go back to that for a second, remember we talked about this situation in the stack as being laminar flow. Well, we only have a pressure drop of about 65 pascals for this 1 millimeter gap. So 65 pascals is a tiny pressure differential, easily producible by a blower. So what if we made it bigger? Like we increase the flow resistance. So we're going to actually make it harder for the gases to get across the stack through this gap. Make the gap smaller. So we know, just looking at the laminar flow, the pressure drop scales as b squared. So imagine you took it from 1 millimeter down to 0.5 millimeter. What would that do? That would increase the pressure drop by a factor of 4, because that scales as b squared. So we go from 65 pascals up to 120, 240 pascals. So imagine making it 1% of an atmosphere. So that's a factor of 20 increase in the pressure drop. We go back to our manifold. This is telling us that if we increase the pressure drop across the individual cells by a factor of 20, then R is going to decrease by a factor of 20 to the 4th power. So if I take 20 to the 0.25 power, that's 25%. So in other words, we go from 1 inch, a 2-inch rate diameter, 1 inch, we now be at a 1/2 inch diameter, which is now getting a lot smaller. So by increasing that flow resistance within each cell, we actually decrease the flow variation across the individual cells. Less resistance in the manifold, we're transferring more of that pressure resistance into the cells themselves. That actually evens out the flow distribution.